In mathematics, equality is a relationship between two quantities or, more generally, two mathematical expressions, asserting that the quantities have the same value, or that the expressions represent the same mathematical object. The equality between A and B is written A equals B, and pronounced A equals B. The symbol equals is called an equals sign. Thus there are three kinds of equality, which are formalized in different ways. Two symbols refer to same object. Two sets have the same elements. Two expressions evaluate to the same value, such as a number, vector, function or set. These may be thought of as the logical, set theoretic and algebraic concepts of equality respectively. Etymology. The etymology of the word is from the Latin equalize from equus, equality in mathematical logic. Logical formulations. Equality is defined so that things which have the same properties are equal. If some form of Leibniz's law is added as an axiom, the assertion of this axiom rules out the particulars, things that have all and only the same properties but are not equal to each other, which are possible in some logical formalisms. The axiom states that two things are equal if they have all and only the same properties. Formally, given any x and y, x equals y if, given any predicate p, p if and only if p. In this law, the connective if and only if can be weakened to if. The modified law is equivalent to the original. Instead of considering Leibniz's law as an axiom, it can also be taken as the definition of equality. The property of being an equivalence relation, as well as the properties given below, can then be proved. They become theorems. If A equals B, then A can replace B and B can replace A. Some basic logical properties of equality. The substitution property states, for any quantities A and B and any expression f, if A equals B, then f equals f. In first-order logic, this is a schema, since we can't quantify over expressions like f. Some specific examples of this are, for any real numbers a, b, and c, if A equals b, then A plus c equals b plus c is x plus c. For any real numbers a, b, and c, if A equals b, then A minus c equals b minus c is x minus c. For any real numbers a, b, and c, if A equals b, then ac equals b c is x c. For any real numbers a, b, and c, if A equals b and c is not 0, then a, c equals b, c is x, c. The reflexive property states, for any quantity a equals a. This property is generally used in mathematical proofs as an intermediate step. The symmetric property states, for any quantities A and B, if A equals B, then B equals A. The transitive property states, for any quantities A, B, and C, if A equals B and B equals C, then A equals C. These three properties were originally included among the Peano axioms for natural numbers. Although the symmetric and transitive properties are often seen as fundamental, they can be proved if the substitution and reflexive properties are assumed instead. Equalities as predicates when A and B are not fully specified or depend on some variables. Equality is a proposition, which may be true for some values and false for some other values. Equality is a binary relation, or, in other words, a two-arguments predicate, which may produce a truth value from its arguments. In computer programming, its computation from two expressions is known as comparison. Equality in set theory. Equality of sets is axiomatized in set theory in two different ways, depending on whether the axioms are based on a first-order language with or without equality. Set equality based on first-order logic with equality in full with equality. The axiom of extensionality states that two sets which contain the same elements are the same set. Logic axiom. X equals YZ. Logic axiom. X equals YZ. Set theory axiom. X equals Y. Incorporating half of the work into the first-order logic may be regarded as a mere matter of convenience, as noted by Eliacute v. The reason why we take up first-order predicate calculus with equality is a matter of convenience. By this we save the labor of defining equality. and proving all its properties. This burden is now assumed by the logic set equality based on first-order logic without equality and full without equality. Two sets are defined to be equal if they contain the same elements. Then the axiom of extensionality states that two equal sets are contained in the same sets. Set theory definition: X equals Y means Z. Set theory axiom: X equals YZ. Equality in algebra and analysis. Identities: when A and B may be viewed as functions of some variables, then A equals B means that A and B define the same function. Such an equality of functions is sometimes called an identity. An example is 2 equals x2 plus 2x plus 1. Equations: an equation is the problem of finding values of some variables, called unknowns, for which the specified equality is true. Equation may also refer to an equality relation that is satisfied only for the values of the variables that one is interested on. For example, x2 plus y2 equals 1 is the equation of the unit circle. There is no standard notation that distinguishes an equation from an identity or other use of the equality relation. A reader has to get an appropriate interpretation from the semantics of expressions and the context. An identity is asserted to be true for all values of variables in a given domain. Congruences: in some cases, one may consider as equal two mathematical objects that are only equivalent for the properties that are considered. This is, in particular, the case in geometry, where two geometric shapes are said equal when one may be moved to coincide with the other. The word congruence is also used for this kind of equality. Approximate equality: there are some logic systems that do not have any notion of equality. This reflects the undecidability of the equality of two real numbers defined by formulas involving the integers, the basic arithmetic operations, the logarithm and the exponential function. In other words, there cannot exist any algorithm for deciding such an equality. The binary relation is approximately equal between real numbers or other things, even if more precisely defined, is not transitive. However, equality almost everywhere is transitive. Relation with equivalence and isomorphism. Viewed as a relation, equality is the archetype of the more general concept of an equivalence relation on a set. Those binary relations that are reflexive, symmetric, and transitive. The identity relation is an equivalence relation. Conversely, let R be an equivalence relation, and let us denote by XR the equivalence class of X, consisting of all elements Z such that XRZ. Then the relation XRY is equivalent with the equality XR equals year. It follows that equality is the finest equivalence relation on any set S, in the sense that it is the relation that has the smallest equivalence classes. In some contexts, equality is sharply distinguished from equivalence or isomorphism. For example, one may distinguish fractions from rational numbers, the latter being equivalence classes of fractions. The fractions are distinct as fractions, as different strings of symbols, but they represent the same rational number, the same point on a number line. This distinction gives rise to the notion of a quotient set. Similarly, the sets are not equal sets. The first consists of letters, while the second consists of numbers, but they are both sets of three elements, and thus isomorphic, meaning that there is a bijection between them. For example, however, there are other choices of isomorphism, such as and these sets cannot be identified without making such a choice. Any statement that identifies them depends on choice of identification. This distinction between equality and isomorphism is of fundamental importance in category theory, and is one motivation for the development of category theory.